Hi, today I'm looking at Leetcode problem number 28. Here we are asked to find a substring in a string. First, I will go over the intuitive brute force solution and then the optimal KMP algorithm. Let's look at an example. We are looking for the substring in the string. Since we get a match starting at index 3, we would return 3. How can we develop an algorithm to perform this search? We could check all the possible starting positions. At first, we would start at the beginning and check index 0. And then character by character, we would check whether there is a match between the substrings. Here, first, second, and third letters match, but the fourth character doesn't, because A doesn't equal to D. Since there is no match, we will move on to the next starting index. Here, A doesn't equal to B, so there is no match, and we move on. Once again, there is no match, so we will continue our search. Finally, we get that the first, second, third, and fourth letters match, so we have found our substring. Now I will code up this approach. So first, I would want to loop through all the possible starting positions. Right now, the for loop goes through every single character of the input string, which isn't quite right. Going back to the previous example, while index 0, 1, 2, and 3 are valid starting point, if we were to start at index 4, there would only be 3 characters left in the string, while the substring is of length 4, so it would be impossible to get a match. So the stopping point will be given by the difference between the length of the string and the length of the substring. In the example, the string has 7 characters, substring has 4 characters. So 7 minus 4 is 3, which gives us the correct last index that we check. Inside the for loop, I want to check if I have a match. And then if I get a match, I will return my current starting index, which is I. So here I will define j, and then I would want to loop through all of the characters in my substring. Then I will check if the corresponding character in my substring does not equal to the corresponding character in the string, then we don't have a match, and I would break out of this for loop. And then to check whether or not we had a match, I will check if j is equal to the substring.length, and if it does, I will return I. This for loop would run to completion only if we have found our substring in the string. And in the end, if we have checked all possible starting indices and haven't found the substring, I will return -1. We have an edge case. The problem states that when we get an empty substring to search for, we would return 0. What happens when the substring is empty would make an excellent question to ask in an interview. The time complexity of this code is given by O(n) times m, where n is the length of the string and m is the length of substring, and the space complexity will be O(1). We could improve time complexity by using KMP algorithm. KMP algorithm does preprocessing on the substring we are matching. Let's go through the preprocessing step first. Given a substring AAB, AAAB, we want to find repetitions, and we would record them in an array. We proceed by adding a character at each step to examine. At first, we just start with the first character. Since this substring is of length 1, there can be no repetition, so we record 0. At the next step, we look at AA. We can see that the first character is equal to the last, so our repetition is of length 1, and we record 1. Now, we examine 3 characters. Note that we are specifically looking at repetitions at the start and at the end. Even though there are 2 A's, the ending character is B, which does not match the first character, so we will record 0 here. So in this way, we are matching suffix with the prefix. Adding another character, we have a at both the beginning and end. So the suffix and prefix of length 1 are repeated. So here we would record 1. Note that inner characters do not match. Going forward, now we have 2 A's at the beginning and 2 A's at the end. So the matching suffix with the prefix is of length 2. Going forward, once again, we would have that the matching suffix and prefix is of length 2. Note, the middle characters do not match, so they cannot be part of the repeating pattern. Adding the last character, now we have 3 characters match. So pattern AAB occurs both at the beginning and end. So we record 3. I will first write up the code to build the prefix table, then go through an example. KMP algorithm constructs this table efficiently in linear time. First, I will initialize my table to be an array with 0 at the first index. Then we initialize I to 1, which represents the index we are looking in the string. And we will need another pointer. So we initialize j to be equal to 0. And j represents the length of the repeating suffix-prefix pair. Then we would do a while loop until I reaches the end of our string. And in the end, we will return the table. Inside of the while loop, we care about 3 cases. If the character at index I matches the character at index j, if they do not match but j is greater than 0, and then the last case that we care about is when the characters do not match and j is equal to 0. I will fill in what we do for each condition as I go through the example. We had a string AAB, AAAB. So here our table right now has just one element 0. We initialize I to 1 and j to 0. So j is under the first character while I is under the second character. So when we compare I and j and they're equal, that means that the repeating suffix has gotten longer than it was at the previous step. So we can increment j by 1. Then we can record inside of our table the current length of the repeating prefix, which would be j. So in this case, I would record 1 here. Oh yeah, and so here I incremented j to 1 and then recorded 1 in the table. And finally, I will need to increment I so that we could go on to examine the next character. Now, when we compare the character at I and j, they do not match. However, j in this case is greater than 0. In this case, we would update j to be equal to the value in the table at j minus 1. In this case, we would get that the value at j minus 1 at index 0 is 0, so we will set j to 0. Notice that we want to give this index a chance to be compared to the current I index, so we will start our while loop all over again and do the comparison. And once again, the 2 characters a does not equal to b, and this time j is equal to 0. So since we have a mismatch, we will record 0 in our table. And then we want to increment I so that we could examine the next character. Now I is at index 3 and j is at index 0, and we have that a matches a. So we have this first case. So we will increment j, then record it in our table, and then we will increment I. Then doing this comparison again, we get that si is equal to sj, so our repeating prefix is definitely has gotten longer. So we will record 2 in the table and then increment I. Now we finally get a mismatch between I and j, so we have b does not equal to a. So we hit this middle if-else statement. We know that this prefix and this suffix here, they were the same and they were of length 2. So we could see if there is repetition of the suffix in our previously matching prefix, and we would jump back to compare the character there. This is what essentially performing this step does. So we would take set j equal to the value of the table at j minus 1, so at 1, which would be 1, so j would move back one step, and then we would compare j with I. And now, since they are equal, we would record once again 2 in the table, and then we would increment j, and then record 2 in the table, and then increment I. Once again, the characters that I and j are equal to each other, so we will increment j, record 3 in the table, and then increment I. And now we have gone through the entire string, so we can return our resulting table. Now let's go back to the first example and search for the substring using the prefix table. Since all the characters of the substring are unique, the table will have 4 zeros. Starting at beginning, we could start our comparison. A matches, B matches, C matches, but E does not match D. Up until letter D, we can look at the substring and we can see that since all the characters are unique, there won't be a repeating prefix and suffix. To save us the effort of matching suffixes as prefixes, we can look up the value at index 3 in our table to get our answer, which is 0. In this case, it means that there won't be a match here nor here, so we are free to move our substring all the way down to start comparing the first character with E. And since the characters don't match, we will just keep moving on. Now, when we do the comparison, all characters match, and we have found our pattern. So the knowledge of the prefix table helps us skip ahead when there is a mismatch, so we can achieve linear time complexity. Let's look at another example. We have already computed a prefix table for this pattern, so let's see how we can use it. I will introduce variables I and j, which will help us keep track of the letters we are comparing. So when the letters match, we can move I and j to compare the next characters. And when they match, we will move them over again. So in this way, when the characters match, we increment both I and j by 1. And we keep going until we reach 2 characters that do not match. We can see that in the substring, just before the mismatching characters, we have a repeating prefix-suffix pair. And if we look at the corresponding value in the table, we see 2, which is the length of the repeating prefix-suffix pair. So it means that we need to move j to index 2 and try the comparison again. Now the characters match, and we are free to proceed forward, incrementing both I and j. And actually, the rest of the characters match, so eventually I and j will reach the last characters, and then we are done, and we have found our substring. So this was another example to try and develop intuition for KMP algorithm. Now let's code it up. So in the main function, I will still need to take care of the edge case, and in the end, if I don't find a match, I will return -1. So first, I will build my prefix table and initialize I and j. Then I will iterate through the characters of the string and substring. So while I is less than string.length and while j is less than substring.length, I will do my comparisons. So I'm going to look at 3 cases. When the character in the string at index I matches the character in the substring at index j, I will increment I and j by 1. Now, if the characters do not match and j is greater than 0, in this case, I will set j to be equal to the value in my prefix table at j -1. And then if the characters do not match and j is equal to 0, then I can just move on and increment I by 1. In the end, if I exit this while loop and j is equal to substring.length, that means we were able to get a match for every letter in the substring. So we have found our substring inside of the string. We would return the starting position of the substring, which would be given by I minus j. And if we don't find it, then we would just return -1. A better way of writing it would be like this. So if we have found the string, then we return I minus j, and I will delete this. If we haven't found it, we will return -1. Now the time complexity is given by O(n) plus m, where n is the length of the string and m is the length of the substring, because we take linear time to build this prefix table, and then we take linear time on the order of n to go through this while loop. Space complexity is going to be O of m because we need to build up this prefix table, which will have its length be equal to the length of the substring. Personally, I have always found KMP algorithm to be quite challenging, so I hope this video could save you some of the pain of learning KMP algorithm. If you have any questions or suggestions, let me know in the comment section, and good luck with your studies!